and how the measurements happen, just quick physics lesson. Then going on to the advantages that the mid-infrared presents versus alternative systems or conventional systems. Then where the mid-infrared fits today in terms of the processes that we're talking about here at this conference. And finally, I'm going to end with some technology breakthroughs that have been happening, some interesting things that have been happening, and some final thoughts. Piggybacking on that introduction, there's a picture of me outside of it, said very large reheat furnace taking oxygen readings, and I'm kind of on like the other side of the industry, now providing semiconductor components. So kind of have like a big perspective on what's going on. So as promised, let's go right into the crash course of absorption spectroscopy. Some of the chemistry inclined people in the room may recognize this diagram. It's the Jablonski diagram. The main takeaway I want people to have is that, consider your molecule. There are certain vibrational modes and rotational modes. When you expose a molecule to very, very high energy, i.e. like visible wavelengths or UV wavelengths, you may get fluorescence or emission. But something kind of cool happens when you expose molecules to longer wavelength light or lower energy light. That's when absorption happens, and then you get different vibrational modes. And we see this manifest in a chart like this. This shows a lot of usual suspects, gases that we're after and where they absorb. Due to these very principles, as discussed before, molecules will absorb specific wavelengths of infrared light, and you can see that on display here. For example, if we're looking at CO2, around 4.3 microns or 4,300 nanometers, it's going to absorb the light very, very heavily, yet wavelengths around it, it barely absorbs at all. And putting it all together, how are we going to measure a gas using light, mainly infrared light? Hopefully you have an IR light source that is producing these wavelengths, and then you have your sample, the gas, and as it absorbs this energy at that specific frequency or wavelength, you're going to get a weaker signal. Then you see this change in signal with an infrared detector. All of this feeds into what we call the Beer-Lambert law. Some of you may be familiar. Something I want everyone to kind of take notice of, because I'm going to be mentioning it later. L down here, the path length. How long do you allow the light to pass through the sample? The longer your path length, the more opportunity there is for absorption. And then you can detect lower limits of gas. And I'll expand upon that a little bit later. So just some quick comments about the components that go into these systems. This is where Hamamatsu comes in. When it comes to mid-infrared systems, there are two main components. One is the quantum cascade laser, and the other, of course, is infrared detectors. Quantum cascade lasers are, as I have in bold here, as old as Gen Z. The first quantum lasers first came out of a Harvard research group in the 90s, weren't really mainly commercialized until the early 2000s. Here we are in 2022, and there are deployments of this technology measuring gas, so the technology is very young. It does come with certain challenges, though. They are made in a batch process, a very specialized technology. However, there are committed vendors that are vertically integrated, of course, like Hamamatsu, that are ready to take on higher volumes. Bringing the cost down and the complexity down will come with volume. And same goes with the detectors. Detector material isn't like an invisible, where you usually just use silicon. It requires a lot of special stuff like mercury, cadmium, indium arsenide, and tinamide. So there are some concerns about the wafer material. Sometimes it needs to be cooled. Creating these types of systems requires a whole lot of expertise. But again, there is a whole bunch of committed vendors who are vertically integrated to take on new challenges. So diving into the mid-infrared itself, for those who may be familiar with optical techniques to start, I mentioned carbon dioxide before. You can measure carbon dioxide using near-infrared wavelengths, so around 1.5 micron or 2 micron or 2,000 nanometers or 1,500 nanometers. However, looking here, you can see the absorption characteristic is so much stronger in the mid-infrared. If you have stronger absorption characteristics, and in this case, it's by orders of magnitude, you can achieve orders of magnitude higher sensitivity in your detection systems. Another cool thing that quantum cascade lasers can do, if you kind of zoom in on an absorption profile of a certain gas and many molecules, these peaks are very, very, very thin. And this is something that the quantum cascade laser can zero in on. You can have a certain wavelength, shift it a little bit to the left or the right, and you'll have absolutely no absorption. But if you hit it right on the right spot, you'll have tons of absorption, again, powering the high sensitivity. So why don't we take a real-world example? Let's say that we're after carbon monoxide, which is a usual suspect in ultra-high purity bulk gases. Well, there's a whole lot of possibilities. I could create a system. It could go over here. It could go over there. Pretty simple. Let's add carbon dioxide to the mix. A little bit trickier. Why don't we add water? Because water is absolutely everywhere all the time. And I can tell you that water is a much bigger headache in the near infrared, and you can tell even in the mid infrared it's a huge headache. So what if I had a laser and detector system that can zoom in on an absorption peak that avoids all the noise? That is how you achieve high sensitivity, and that is the power of the mid infrared. So some comments about other technologies that are out there. Most commonly gas chromatograph or ion-based technologies or mass spectrometers. Been around for decades, if not a century in terms of gas chromatograph. Great analytical techniques. Absolutely nothing against them. And in the end, you're kind of looking at the same profile. You have a single unit that can analyze all of your species all in one box. They can achieve very, very high sensitivity. However, there are important drawbacks to consider, especially in the case of GC. You have consumables, and I heard earlier today about the fourth version of a helium shortage. Helium is an associated cost, and also there's calibration and some labor and upkeep involved with these systems, so the cost of ownership can also be a concern. I'm thinking about a laser system, or in general QCL and a detector system. You don't have a lot of these issues. There was in the last session there was talk about FTIR and other analytical systems. When it comes to a laser-based system or TDLAS, tunable diode laser absorption spectroscopy, you don't have that side stream. You don't have that gas cleanup. You don't have filters. You don't have moving parts like in a FTIR system, and you have a complex moving mirrors. You don't necessarily need the reference cell. This is a measurement, may not be the measurement to make, but you can simply have the laser shooting across a gas stream with a detector on the other end, and there is your measurement. Because you're getting that wavelength right away, and all you need is the detector to apply the Beer-Lambert law. So it opens up a whole lot of possibilities for quicker, more agile systems. So let's put it all together. Of course, GC, mass spec, again, absolutely nothing against them. Super powerful analytical techniques, and mass spectroscopy remains one of the most powerful analytical tools that we have in our toolbox. But something that Archita was talking about before, we need to perhaps combine things or think of new ways to go, because there are drawbacks with the consumables, the maintenance, the cost of ownership, and also one must consider risk to process. If you have all of your species being analyzed with a single system and that system goes down, that's it for your process. And looking at, say, optical infrared, the upfront cost is higher. The systems are more expensive, as you can tell from how specialized quantum cascade lasers are. And also you commonly need to purchase 1 unit per species. So the upfront cost is there, absolutely. But what you gain is you don't have to deal with the consumables. They run a lot faster. They have much lower cost of ownership. They don't nearly need the upkeep or the maintenance or the calibration. And if one analyzer goes down, that doesn't necessarily doom your process. So with all these factors considered, of course, every situation is different. Every process is different. More times than not, you're looking at an ROI of about 3 years when you're looking at a laser analyzer system. And again, every situation is different. Key takeaway is you can look at a very strong ROI with a laser system. So why don't we dive into what's going on today, what's the conventional technology, what's going right on right now when it comes to laser systems and mid-infrared systems. Most commonly, you'll see them deployed, and this is a couple of familiar scenes for, I'm sure, many of you. You have the air separation units on site or your bulk storage supply, and also in the fab environment. Archita really went into this in terms of airborne molecular contaminants. But on the ultra-high purity side, you're commonly looking for contaminants such as carbon dioxide or carbon monoxide. And the airborne molecular contaminants, you're looking at HBr, HCl, HF, ammonia. So in terms of going into the bulk gas side of it, again, you have your ASU, your bulk tanks, you have a purification stage, and in this case, you could have your little stack of laser analyzer systems, and then it could go to process. And I'm going to show some quick examples. This is courtesy of Tiger Optics in terms of readings that they took over the course of 24 hours. But before that, this is just, I'm just a curious guy, and whenever I see a little black box like that, I'm wondering, what's going on in there? What is this little thing? And this is kind of like a crude setup of something that you would see in this box. You need electronics to power the laser, and you have a laser. And the key thing I want everyone to look at here, you have a multi-pass cell. This is essentially something that reflects the light back and forth many, many times. If you all recall, path length. Path length is absolutely key to achieving high sensitivity. So this is kind of what's going on. You got the detector, you got a multi-pass cell, and of course the laser, and you need a whole bunch of fancy stuff to power it. But of course, this is all miniaturized and optimized in the units that you see out there. What you will see commonly in terms of the technology that is deployed today, available today, is cavity ring down spectroscopy, or CRDS. Why is this so popular? It's scalable, it's verifiable, and got really, really popular in a lot of academic settings. There was a lot of national research behind this. And essentially what it achieves is with a high finesse optical cavity here, you're achieving a very, very, very long path length. Like the light bounces back and forth over and over and over and over again. And if there is some sort of gas inside, the signal is going to decay X amount quicker, right? And since this path length is so incredibly long, tiny changes, even a few molecules within the space, is going to affect this decay time because, again, the path length is a huge part of the Lambert law. So as promised, some of the data that we're looking at. So this is the power of analyzers. 24 hours of operation, and this is parts per billion with a B. So that is carbon monoxide inside of high purity oxygen. And the detection limit is measured as going into PPT, which Archita was talking about before. We're going to need to get to these higher orders of magnitude, not only parts per trillion, but in the future parts per quadrillion. Looking at carbon dioxide and nitrogen. So if we recall the principles we talked about before, dodging sources of interference, that high specificity. This technology is versatile, so doesn't matter if it's oxygen in the space or nitrogen in the space, as with carbon dioxide and nitrogen, you're going to be able to hit those absorption bands right on, and you don't need to care about those sources of interference. Also introducing carbon monoxide and nitrogen, same with those peaks. And you can see here over 24-hour operation, you can these spikes of carbon monoxide were introduced and they were detected very consistently and reliably. Going back to the airborne molecular contaminants, this model is courtesy of Picaro. This is just a quick model of, if you have a clean room, how you can kind of guide everything into a single laser system. And some of the usual suspects can be detected in systems like these, like HCl, HF, and ammonia. And I have a quick table over here that shows over the past decade or so how standards have gotten tighter. And for good reason, as we talk about the exposure and the complexity, and Archita was talking about this before, standards get tighter, and we can only expect it to get tighter as time goes on. And airborne molecular contaminants are, of course, no exception. Expanding a little bit about what I was talking about before in terms of measurement times. Now, if something undesirable is getting near your process or in your clean room or in your fab, I assume everyone in this room wants to know about it as soon as possible. Well, if you're looking at certain ion systems or mass spec systems, That isn't necessarily the case. You're going to be waiting perhaps minutes, perhaps hours, also attaching calibration and maintenance. With a laser analyzer system, and today with CRDS, you're looking at readings on the order of seconds, and it's running all the time, continuously, 24 hours a day. So if you're worried about contaminants in your system, you want to know as soon as possible, look no further than a laser system. And of course, they're sporting very high sensitivity on the order of parts per trillion as well, which is exactly what you want. So as promised, some of the cool stuff that's going on. The technology is very young. Quantum cascade lasers remain very popular in a whole lot of research. This is a recent breakthrough in the parts per quadrillion measurement for decaying carbon dioxide. The setup down here is a little bit fancier, and this is an academic achievement. However, this exhibits the possibilities that lie ahead for quantum cascade laser systems. For all the principles that we talked about before, hitting the absorption head, skirting sources of sensitivity, really taking advantage of that higher absorption factor. The potential, there's much more potential ahead for increasing the sensitivity of these systems. And here's an example of an ammonia measurement made in the open atmosphere. This is a group led at Princeton, led by Mark Zonlow, who I work with quite a lot. And they made a system that is deployed in the middle of a field. And they are achieving ammonia measurements on the order of parts per billion. Now, they are achieving parts per billion sensitivity in the middle of an open field. You have to incorporate wind and humidity and other contaminants. And even with all these factors that make the measurement incredibly hard, they were able to achieve parts per billion sensitivity. Can you imagine what you can achieve if you can have a closed, clean system looking for ammonia? And first I want to point out, again, creating that path length over and over and over again, you'll see a lot of similarities in these systems. And something that I wanted to show, I've been talking a lot about absorption and interference, and now we can see it right here in real life. In the middle of that field, you have a whole bunch of stuff, and they have absorption peaks across this wide range of wavelengths. That definitely is going to present a challenge. However, coupled with the laser and the detector, and you normalize the signal, you can see that the signal is now dominated by the ammonia absorption. We see that effect of dodging interference right here. And also to note, something that the research group found, as analyzers were placed closer to the road, smaller distances to the road showed massive spikes in carbon monoxide as well. So this just goes to show if there is an absorption band in the mid-infrared, you can create a system to find that gas and analyze that gas at extremely high sensitivity. So just some final thoughts. The optical science is well established, and there are a lot of researchers out there pushing the limits of sensitivity. Again, the technology is very young. The component side is improving as well. When it comes to parts per quadrillion, that's what we're aiming for as well. We're looking to work with people who want that, and we're looking to make it happen. These components are specialized. There are vertically integrated manufacturers, but they're few and far between. But we're looking to expand heavily on this technology and improve it, and driving the volume is key. As volumes go up, we will be able to do more. We'll be able to optimize with the batch process, and that's going to lead to better scale and lower cost and higher performance. Although, if you're looking at continuous analyzers, they are going to provide you are going to look at a higher upfront cost. You are going to need an analyzer for each separate species. In many cases, they could be a complementary system. So if you're looking at one or the other, you're definitely looking at an explicit ROI, lower cost of ownership of the laser system, because you're not dealing with those consumables. You're not dealing with that maintenance and calibration. And on top of that, you're mitigating your risk, because one analyzer down doesn't doom your process. And again, you're seeing much, much, much faster measurement cycles with a laser system. So if you're interested, ask your gas vendors, ask a spectroscopy specialist, ask the analyzer companies. You can even ask component companies, like myself and Hamamatsu. We're all nerding out about this stuff, and driving the conversation sooner is what's going to make things happen. Collaboration is what's going to make things happen. And again, as the standards increase, the mid-infrared analysis is key. Not only are we going to need higher sensitivity, but we're going to need more reliability, we're going to need faster measurements, and we're going to need more economy of scale. And with all the facts I presented today, I hope I made the case for the potential of mid-infrared. So thank you very much.